Okay, the final talk of the session is about Cerisier, presented by Denis Carnier.
Okay, hi everyone. So thank you all for being here. I'll be presenting Cerisier. You may be wondering what these words mean, like attestation and capability machines. So let me just motivate this using a running example. So you were to imagine a client process that's running on a particular machine, think of a CPU, and at some point it gains sentience and dares to ask a very difficult question, right? Douglas Adams worded this beautifully. What is the answer to the ultimate question of life, the universe, and everything? And so like any good piece of software, what it does is it's delegating or outsourcing the computation to a lesser privileged component running somewhere else on this machine. The component here is called deep thought. This is analogous from the book. Maybe you've read it, maybe you've not. But what it does is it runs this computation for a couple million years and finally returns an answer. Unfortunately, the answer is bogus. So why did that happen? Well, inadvertently, when we outsourced the computation, we compromised the integrity of the results because an adversary was really in control of the kind of software that was running on top of the machine. And so what the client really needs from the, is there a microphone problem? Oh, no. What the client needs from the machine is a way to carve out sort of specific, from the adversary-controlled memory region, an area of memory that is in some way impenetrable. You can call this an enclave. I'll draw a castle around this memory region to signify that it's impenetrable. And importantly for us, this happens sort of on the fly. Really, we're revoking memory from the adversary and giving exclusive access to this enclave component. The hardware security people refer to this as late launch or a dynamic root of trust. And so this solves our problem because now this enclave basically gets a specific cryptographic key with which it can sign answers. And on the other side of our example, the client can sort of verify who owns this key that signed this answer that I got, and the machine will say, well, it belongs to deep thought. Now, importantly in this story, the signature, or the key behind the signature, it must be linked to the identity of deep thought. In particular, here we will mean that it comprises a hash of its source code. There's some other things which I'm omitting, just for brevity. So let's make this more concrete. You guys love code, so I'll instantiate the client and say that we invoke the adversary, we'll jump to it and ask this very difficult question, and then we'll eventually store the result in this res variable. On the other side, the adversary, what it does is it sort of registers this deep thought enclave by calling this init primitive, which sort of revokes some memory somewhere in the adversary region, and it will store the result in this enclave variable, and you can think of this as a kind of closure, which it then invokes, or maybe a function pointer which it invokes. And finally, once this closure finishes, the result is returned to the client. So deep thought itself is a very complicated process, right? So it thinks for a couple million years and then finally returns 42. But of course, we now know that we have this fancy feature, this primitive on the machine that lets us generate a sort of globally unique signing key using this genattest key primitive. And then, of course, we mustn't forget to use that key to actually sign the result. So coming back to the client now, we can unpack this into both the answer and the key. And then importantly, we need to check that the key actually belongs to deep thought, right? Otherwise, an adversary could have picked a different key to sign the result with. And so the way we'll do this on the client side is we know, of course, what the source code of deep thought is, so we can sort of hash its source code to obtain a static identity, and then confirm by calling this a test primitive that the machine has really registered with that specific enclave, that specific key. If that's not the case, we'll abort. And then finally, we'll be able to verify that really the answer that we got is equal to 42. Now, the problem statement is how can I, as a proof engineer, verify the safety of this example? So in other words, provided that the machine did not actually crash, how can I prove that the assert can't fail? This is not that trivial. In particular, we're jumping to and from an arbitrary adversary. This adversary is somehow revoking access to its own memory region to set up the secure region. And then there's this attest primitive that somehow allows us to interact with the machine to infer the identity. And then all this to somehow conclude that there's this property that holds for the answer that we got back. So how do we reason about this? I'm going to come back to this zoomed out example once more. Let's break it down into manageable chunks. So the client code is really known code. We can apply standard Hoare logic or Hoare-style program logic to verify it. The only exception is really the interaction with the adversary, and for this we basically define a logical relation that captures this intuitive notion of what the adversary can do, sort of giving an over-approximation of all the things that it could deal with, or what the worst thing is that it's capable of doing. But then finally the difficult part is the enclave itself. So how do we verify this? And this is really the key challenge and what I intend to devote what time I have left here. So it's the solution that we came up with is basically 3 ideas. So the first is we need a way to reason about memory revocation. We need to ensure that we have exclusive ownership, or that the enclave has exclusive ownership over its own memory region. Second, we need a way to deal with cryptographic signatures, right? We need some way of reasoning that sort of signatures mean something for specific signed values. And finally, there's this attestation problem, which is the client has this specific signature and it wants to know who does this key belong to, and the machine says, oh, that key, that's for deep thought itself and nobody else. These first 2 ideas were basically reusing techniques from the literature that we adapted, and the third one is really the most novel part of the paper, I would say. So the first part, so reasoning about memory revocation. Earlier I drew these kind of arrows to mean that the adversary had some way of still getting into this deep thought enclave, and we need a way of getting rid of these arrows. So in order to explain this, I need to kind of lift the veil a little bit on the underlying machine semantics that we're dealing with. So very operationally, we're dealing with something called cherry tree, which is which was published at EuroSMP in 2023. It's a kind of ISA extension implemented on top of a Cherry RISC-V processor. Cherry RISC-V is, of course, this capability hardware-enhanced RISC instruction set. And for those of you unfamiliar with capability machines, on this style of architecture, sort of traditional memory pointers, they're replaced by something called memory capabilities. And what this means is you can think of it as a for tuple. There's some permissions that you get with this memory capability. In this case, it would be something like read write, and then there's various bounds. So there's a B for a begin address, and an E for an end address, and then of course the pointer address itself, A. And then the machine will actually dynamically check these bounds during execution to ensure that the pointer is really pointing inside this region and that you have the right permissions to do what you want to do. In case you want to dereference the memory, you need a read permission, etc. But so Cherry Tree specifically extends Cherry with sort of a minimal set of extra features to, on top of this sort of memory isolation idea of Cherry, support this enclave model that I've been sketching before. And so what it does is it adds something called sealing and sealed capabilities. They essentially allow to sort of close over memory capabilities, and they model a kind of symbolic crypto. And then, by the way, this is not a new contribution for Cherry Tree in particular. Sealing capabilities already existed. But also we need a memory sweep mechanism. When the revocation happened earlier, we need a way to be able to go over all of memory and all of the register file to ensure that nobody still has capabilities that point into the region that we want to reserve. And then there's some extra special purpose machine state to keep track of which enclaves have registered, and in order to hand out sort of fresh keys. So for this last part, maybe I can go back to the example from before. So when the adversary initializes this enclave, and the enclave calls this genattest key primitive, there's a kind of table that keeps track of enclaves that registered that specific key with that specific enclave. And then on the other side of the story, when the client actually gets that result back and it calls this a test primitive, it's sort of verifying that that key really belongs to the enclave it's interested in. And so reasoning about this is kind of analogous. This is what we realize. It's analogous to kind of stop the world garbage collection, where you have a bunch of GC routes and you're kind of traversing and sort of freeing up memory. And Gil Her, I think is his name, or pronounce it his name, together with Derek Dreyer, have already come up with a program logic to deal with this. So sort of roughly what they do is they have memory addresses which they now index with a logical version, and when sort of the stop the world garbage collection happens, the specific logical versions are bumped to hand out new points to chunks. So we borrowed this for our capabilities. And then secondly, for cryptographic signatures, there's this seminal paper by Sumi and Pierce that associates logical predicates with signing keys, and this is precisely the kind of thing that we needed here for our symbolic crypto. Roughly, because the keys cannot be forged, so we can sort of conclude that all values signed by a specific key have a sort of logical predicate that we can associate with them. And then the final sort of ingredient in the mix is this attestation reasoning machinery. And for this, we came up with sort of 3 key elements that we kind of combined to be able to do this end-to-end proof. In particular, the first part is this custom enclave map. So we have a logical map. And what it does is it kind of associates with a static identity for a particular enclave logical predicates. And then we also register a system invariant that sort of keeps consistency between the machine state and its logical state. In particular, on the left, you have this key, which is very operational. It's a specific key that was assigned by the machine for an enclave. And the machine keeps track of this using this E-table with the identity of the enclave. In turn, the custom map couples this identity with a logical predicate, and all the while we use this idea from Summian Pierce to tie the key to this predicate as well. And then the third ingredient we need is a custom enclave contract. Basically, we need to ensure as the proof engineer that our enclave is really only signing what we know are sort of good values, or values that represent that respect the signing predicate. And it's also important that we verify that we're not actually leaking our key, because otherwise the adversary could sign arbitrary values with our key. So how does it apply to our example? I'll maybe come back one last time. So the custom enclave map, we can sort of instantiate it as having a single element that maps to DT, that's short for deep thought, a logical predicate that says any word signed will be 42. And then the contract for deep thought itself is you're only allowed to sign values that are equal to 42, and you never leak your key. And for the no code, we can use a system invariant. And so to sketch the proof, initially on the top right, we have this custom enclave map. And then we use this program logic to verify the client code. We model the interaction using the logical relation from earlier. And then the enclave proves its enclave contract, ensuring that it only signs 42. And now our invariant is actually holding, like keeping this all consistent. And so when this client receives this message from the enclave, it can actually use the invariant to determine that the value will be 42, completing the proof. I believe this sort of relatively intuitively captures sort of what you want to expect in the proof. If you're not satisfied by this example, the paper has a bunch more stuff. So we do things like mutual attestation, where you have 2 enclaves that are mutually distrusting of each other, and inside the adversary they have to establish trust. This induces a circularity because essentially one enclave requires knowing the identity of the other enclave and vice versa. So we need a way to break this. And there's also another case study on a trusted sensor which roughly models MMIO. We don't actually have MMIO in the machine model, but it basically is a stateful example. And there's a second enclave that then processes this sensor's data so that we can conclude things about it. So to conclude the talk, we basically did this, we designed this program logic for attestation. We are able to establish end-to-end theorems for these examples that involve both known and attested code. And if you want, there's more complex case studies in the paper. Finally, everything is also verified in Iris in about 35,000 lines of code mechanized inside of ROC. And with that, I want to thank you for your attention. I'll be happy to take any questions you have.
Question?
Yeah.
So I haven't understood yet the motivation for introducing the enclave-specific key. It would seem like instead you could have an abstraction where there's some kind of communication channel between the enclave and the client code, and the communication primitive returns the ID instead of the key. Where you have tuple AK, you get the tuple A ID instead, and then you've saved some steps of processing. What do we lose if we do it that way?
So the key in particular is needed because we cross the sort of untrusted boundary. We have no secure channel, essentially. That's the thing we're missing. So the key is really allowing us to cross this adversary. Like we have this adversarial boundary between where the enclave lives and where it wants to communicate with the client, and we have no sort of secure channel. The key is a sort of way to establish a secure channel.
There's some other more global key involved in the attestation mechanism?
So the key is global. So the attestation key that the enclave gets is global with respect to the machine. It's unique.
Got it. Okay, I might have to bug you about this offline.
Okay,
thanks.
That sounds great. Looking forward to it.
Any other questions?
Sorry, can you speak up a bit?
Can you speak with the mic? Sorry.
There's one over
there.
here.
Is it on? Yeah. What about the crypto primitives themselves? What do you do about that? Is that also verified?
So it's a symbolic crypto. So.
But you can execute the system, right?
Yes.
And what concrete crypto do you use?
It's a symbolic crypto in the sense that so the machine has capabilities on it. They're kind of these abstract objects, and there's kind of an operation to sort of seal these capabilities. So there's no actual 256-bit encryption key that exists. It's kind of just a tag bit on the capability.
Oh, so the signing is not really a cryptographic signature?
Yeah, no, exactly. Yeah, so it's kind of a machine primitive to encapsulate a memory capability.
That makes more sense. Yeah,
Thank you. Yeah.
We still have time. Other questions?
Maybe we can grab an early lunch.
Okay, let's thank the speaker again.
Thank you.